Yeah, another draft physics video presentation. Just keep on coming. Um, so anyway, we'll do some comments, and I think I can give you some insight into where the fatal error was committed and where all this crap follows from. So maybe we'll do that first, and then we'll read this convoluted comment that really has nothing to do with any actual experiment again. Just more, let's do some mathematics to prove it, even though there's no experiment that can prove it. I mean, it's just, why bother? So I'm going to show you a Professor Lewin example, okay? I mean, it's not great, but it illustrates enough of these points. So the PSB guy or whatever has left a comment. I deleted it because it's just a regurgitation of exactly the same assertions he made in other comments. He just keeps saying that I have some obligation to prove the non-existence of his God. I don't have that obligation. It's your obligation. If you say momentum isn't conserved, then show it. But anyway, because I can show you every experiment I know of where it is. So it's just horseshit. And the whole plus and minus thing is just such a pile of crap. Oh, energy isn't in a direction. All right, so anyway, so the example is going to be shown is that you have a spring compressed, okay, and you have two objects of different masses, okay, and you release the spring, and they shoot off and do their thing, okay. Now, that can be thought of as a pressure in this direction and a pressure in this direction. And the truth is, what Professor Lewin will show, other demonstrations will show, is it doesn't matter that this has two masses and this has one mass. Exactly half of the F, okay, here's the F, half of the F is going to go over here in this direction, and half the F is going to go over here in this direction. So half the joules. Let's say the compression of the spring is 500 joules. We're going to get 250 joules of energy will go this way, and 250 will go this way. It matters not, okay, that this one's heavier. It doesn't mean this one's going to go away with more energy. This one's going to get exactly the same amount, okay? So if it was water, okay, they both get 1/2 the gallon. This one gets half, this one gets half the gallon. There's no this one gets more or this one gets less, this one goes off at some other and so the velocities are going to be exactly inverse, okay. The momentum will be conserved, the velocities will be exactly inverse to the masses. So we could say this one's going to have a 1v and this one's going to have a 2v. The numbers, we're going to add up 3 on each side. The mass and the velocity are equal contributors. Now all I have to do to this experiment to show where the fallacy begins is let's just convert this pressure into pressure this way, okay? So let's just bend the pressure. Now we're going to talk about gravity. Gravity doesn't do this split the F in half thing, okay? When you're in gravity, it's not an explosion and that's it. It's not a spring, pow, that's it. It's not a punch, pow, that's all there is, pow. Gravity does this, okay? Gravity is constantly punching, all right? It's constantly springing. It's a spring that just keeps going bang, 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 bang. And you can't run away from it. So it's a spring that's banging back and bang, 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 bang. And you can't get away from it. No matter how far away you go, it's still hitting you. So gravity is nothing, absolutely zero like an explosion. So it's nothing like a rocket engine, okay? Gravity is nothing like a spring, okay? It's nothing like a magnet and another magnet. It's nothing like any of these things. Well, let's not put the magnet in there, but that's a little different. So that might be more similar than I'm appreciating. So all the other ways we create momentum, rubber bands, it's one shot. They expand, they pop your energy, and that's it. It doesn't provide some constant force. It doesn't bang, 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 bang you. It doesn't do any of that stuff. So it has a pop, pow. The two entities are now going to separate, okay, and they're going to separate by splitting the force evenly between them, and the momentums will remain the same. Momentum, same momentum. I don't know how to I don't know how to say same momentum, but it'll always be the same momentum. So whether I make this 3 m's or 10 m's or 500 m's and I make this 1 m, it doesn't matter. They're going to split the force evenly. But when they're in gravity, now the game is different. So now when we're watching these things go down, their velocities can't be different. Okay, they fall with the same velocity. Velocities can't change. And we know the masses can't change. What's going to change here, right? Something, we have changed the masses. But the point is they're going to fall at the same rate no matter what their mass is. So the only thing we can change is how much momentum they're collecting. That's what we're going to be changing. So gravity is a force that keeps hitting. And the smaller the mass, the smaller the force. So they're not splitting the force anymore. The heavier you are, there's a huge bias. So it's not half over here and half over there. So the heavy thing is going to get 2/3, and this one's going to get 1/3, you could say, something like that. These aren't completely accurate proportions. But the idea you can understand, this is like having a bucket a certain size. So the smaller mass is actually a smaller bucket, and the bigger mass is a bigger bucket. And you can understand that more stuff, there's a constant rain coming down, this one's going to collect a lot more water in the same amount of time that this one's collecting it. That's why they're falling at the same rate. And that's why when this one lands, it's going to have more momentum, is because it collected a lot more of the force. Because its bucket is huge and this one's is small. So this one's going to land with a little bit of momentum. This one's going to have big momentum. We use the big M's. Because this one collects more force. So in the same time and the same distance, it doesn't really matter, this one collects much more of this force. So this one took all this much of the force, and this one just gets this little tiny bit of force. Where in the case of this, okay, this other example, the force is perfectly split in half every single time. And so this is what confused them in the 1700s. Okay, the 1700s, they weren't Einsteins yet. Okay, they didn't, So they keep thinking of this gravity thing, and they keep trying to bend gravity into these other circumstances, and they're just getting these two fundamentally different processes confused, like they're the same thing, like they're doing the same thing, like gravity is just like an explosion, or gravity is like a spring, or this, like they're all supposed to be the same. They're not the same. Gravity functions as a constant force, and it's completely, how much force you get depends on your mass. Okay, the more mass, the more force. All right? In the other case, mass has nothing to do with it. Okay, I don't care what your mass is. I'm just going to split the force in both directions. And that's all that's going to happen. You're always going to get the same. So this relates to the idiot, okay, the PBS guy, the PSB guy, because he's making this assertion that the momentum's different. I take the same spring, and he says the same spring compressed the same amount, okay, I put a different mass on it, I get different amounts, okay, of momentum. He's saying I can get different amounts of momentum by just putting a different, 2 mass versus a 1 mass. Clearly no experiment demonstrates that, and clearly the Professor Lewin experiment is exactly the same thing, really. You're just putting this object on this side of the spring, and you're finding out that you're always going to get the same amount of energy in both directions. You can't change how much energy goes in. So just like these two are equal, in terms of their momentum on this side is the same as the momentum on this side, that's the same thing as just saying if I put a brick wall here, and only one side and only watch one side, it's still the same momentum. I can never get a different momentum. Never, never, never. It always has to be the same momentum. The spring is producing the momentum, and it can only produce the same amount of momentum that way as it produces that way. It can't do anything else. It'll always be the same. Doesn't matter how disproportionate it is. Doesn't matter whether, again, it's a little bullet it's shooting or it's shooting a bowling ball. Doesn't matter. Same momentum. All right. So I think that should give you some illustration. Obviously, these things are visually, visually you say, oh yeah, well I know bullets kill people, and I know bowling balls, going a half meter a second aren't all that threatening. But if you really thought about it, if you really just thought about how you could just convert one into the other, I just slow the bullet down and make it fatter and fatter and fatter, and you can sort of see that, well, I make the bowling ball a little bit smaller, that I can make the two meet somewhere, and I can realize that, yeah, if I have this size and I double this size and I have this size and I double this size, I'm just going to get one object going one speed, and they're going to meet. They're going to be the same baseball. If I same grapefruit, I can make the same grapefruit out of the bullet and the bowling ball. It'll make the same grapefruit kind of thing going a certain speed. I can see that I could do that if I thought about it. So if you give it a little thought, you can get it. You can figure out how this all happened. This is just a simple mistake. They thought all force was the same. Obviously, this force, the rubber band, the spring, the explosion, is very different in how it distributes energy than gravity. Gravity is a very different force than an explosion or a spring or a rubber band. And you can't just make an equation and say F equals ma, okay, and I'm going to interpret that to mean it's a constant force all the time. It's always gravity. Every A is gravitational force. No, these A's are not gravitational force. The acceleration when kinetic balls hit each other is so instantaneous that you can't even consider it a thing. You could never say, oh, let's consider this very important A that happens. It's irrelevant because we know all the momentum is transferred. We know it goes right in there, right out of there, at exactly the same velocity here, acceleration, deceleration. Can't mean anything because I get exactly the same momentum. I get exactly, even if I use the kinetic energy formula, I know I'm getting exactly the same kinetic energy here as kinetic energy here. See, if I don't change the mass, then the kinetic energy formula is coherent. But as soon as I change the mass and velocity ratio, it goes wacky. So as I stated before, the kinetic energy formula gets the right answer once a day. And it only gets the right answer when I make the mass consistent or I make the velocity consistent. If I change either one of those, then the kinetic energy, momentum won't equal kinetic energy. Momentum will only equal kinetic energy when I have exactly the same mass or exactly the same velocity. Ratio has to be the same. I shouldn't say the same, I should say the same ratio. Alright. So now I'll read the stupid comment. I don't know if I want to read. I'm not going to read all this mathematical crap. I'll just try to explain why his premise is horseshit. Has nothing to do with anything presented. So he says, she's wrong. Well, it's great that at least you're saying something's wrong besides me. Thank you. When she says half the energy was lost to heat and deformation for the inelastic collision. Well, frankly, that's going to be the excuse most physicists give. So you can pretend she's wrong, but I don't see you arguing it anywhere. No one thinking of the definition of acceleration. Well, you think you have the definition. It's a change of velocity over time, and that's all it is. It's not a big deal to figure out what acceleration is, right? I mean, it accelerates progressively. That's the other thing that's kind of funny. People measure the change in velocity over 1 unit of time. Well, every unit of time is going to be a different change in the velocity, in the sense that once you've acquired the velocity, especially in gravity, 99% of your velocity isn't your acceleration anymore. It's the velocity you gain from your previous accelerations. So your current acceleration is still just this tiny distance that you're gaining. The rate of the gravity, half the distance of the rate of the gravity. So it's a tiny contribution that's being made in each second of time, but you're adding up all the cumulative velocities that you keep acquiring. You keep doubling your velocities. Well, it's not even doubling your you're exponentially growing your velocity until you reach your terminal velocity. Anyway, no one is thinking of the definition of acceleration, question mark. I don't even know what that means. In her, I mean, I don't know why the question mark's in there. It doesn't sound like a question. Anyway, in her example, she changes speed without taking into account any retardation, acceleration. That's an error. No, it's an error on your part to think there's any retardation or acceleration problem. And the Newton's cradle proves there is none. You can't have a more dramatic agitation, that you have a complete deceleration and you have a complete acceleration of a new body, and it doesn't take away any of the momentum. I mean, if you take away the atmosphere, that thing goes a long time. So the actual interaction forces are so minor in terms of stealing any of the energy that you could say they're not worth considering. So for you to say that half the energy was lost to the deceleration and the acceleration process can't make any sense to anybody rational, because Newton's cradle wouldn't work then. All right. The missing energy is due to retardation of mass 1 and acceleration of mass 2. So he's basically just saying the fact that you have to slow, and in the train example, you're not even stopping anything. So it's not even nearly as dramatic as Newton's cradle, right? Newton's cradle, you're taking all the energy from one object and smashing into another, giving it all. In the train example, at least this object never stops. So it only decelerates a little bit, okay? And then they both go off and you have to accelerate this one. Now, clearly Newton's cradle is telling you acceleration and deceleration don't mean anything. They don't cost any energy. You don't lose energy to accelerating and decelerating. Not at all. None. None besides the fact that you have decelerated, okay, or you have accelerated. But it doesn't mean you have to lose any of the energy in the process of transferring those things. Obviously, if you're decelerating, something's acting against you and you've lost your momentum. The point is we're talking about how you're giving it to something else. We're not talking about heating the road. We're not talking about heating your brakes. We're talking about something else as a force slowing you down, and you're going to transfer energy with that thing. You're not losing any energy in that process. And Newton's cradle proves it. All the experiments, frankly, prove it. So what you're saying is just meaningless mush, in my opinion. Change the speed, acceleration, retardation force during short time distance. So again, we know this is time distance has nothing to do with these transfers. They can happen so quickly. Newton's cradle happens so quickly. If you just put one ball in the middle and drop one over here, right? It's the transfer is at the speed of sound in steel for a distance this big. It's such a tiny instant of complete transfer. Okay. Time, distance, work performed both for retardation and acceleration. So he's considering those things work, that is, they require energy, that therefore they would steal momentum. You can't do work with something's momentum and then claim you conserve the momentum. That is, you didn't use it. So it's just nonsense. Mass 1 gives away kinetic energy during the retardation, and mass 2 receives the kinetic during the acceleration. So again, you can't say that. It can't give it away and gain the same kinetic energy. Here you have kinetic energy losing and you have kinetic energy gained. What sense does that make? Absolutely zero. Alright, so he does this blah 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 blah. All this shit doesn't mean shit. Where Vm is the mean velocity during acceleration retardation. So again, there's no mean velocity during the acceleration of a Newton's cradle. There is none. You can't measure it. You can never see it. You'll never find it. The ball just almost instantaneously leaves with exactly the same velocity. The process of acceleration is so minute, so you could never even detect the moment of it. It's so fast. And here you are doing your formula. You don't see how horseshit this is? Oh, amazing. Blah, 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 blah. Where Vm is the mean velocity, okay. We have energy, blah, 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 blah. We've already proven the point, okay? You can't have it both ways. If you say energy was lost, then you have to explain how you kept the momentum. The momentum was your only source of energy. That's it. If you're going to lose some, you can't keep it. Duh. If you're going to transfer it to something else, you can't put it in the bucket. And if you want to reverse the circumstance and say you kept the kinetic energy, well, then you have to create more momentum. Then you have to say the thing after the collision has more momentum. How can it have more momentum? That's not possible. I mean, you people are just, you're just intractably, insensibly crazy. Using an example in the video, mean speed during transmission. So this is where he's somehow saying we ended up not losing as much energy as we thought because we made more momentum. So he's going to give the second object more momentum so he can justify his silly mv squared nonsense. So he's just saying, okay, energy retard. 108 joules of energy retard. How does that help you? Energy to acceleration, 36. So, you know, I mean, so he's trying to come up with 100. He's trying to come up with the 150 joules he needs to account for all that losses. But you can't do that without creating more momentum. So it's not going to work. So anyway, the total energy loss from acceleration retardation work, 72 joules. So he's just making up a silly story that is proven every day by a Newton's cradle that nope, there's absolutely no same kinetic energy leaves, same kinetic energy in. How can there be a complete transfer, complete deceleration, and complete acceleration, and you have exactly the same amount on both sides of the equation for both momentum and kinetic energy? Let's understand, Newton's cradle is the two equations work out just fine, but you're using the same exact mass and the same velocity. So everything stays just fine. You don't have to worry about the conflict between the two formulas. So how do you say that this process happens when there's no evidence that it happens in Newton's cradle? There are no losses to deceleration and there's no losses to acceleration. It doesn't work either in momentum or for kinetic energy. There's no evidence of what you're saying is happening. That's all I can say. Absolutely no evidence. You're just theoretically posing some mystical way that the energy disappeared in some mystical way through the process of banging into each other. Woo woo, woo woo woo. Okay, it's not anything like a good enough explanation. Alright, so let's get to the Professor Lewin and then we'll do the assholes comment. Yeah, so I'll pause for a moment. Alright, should be back and such. So this is Professor Lewin. He's going to do, he did the sliding thing with the same masses, and now he's going to do the sliding thing with two masses. So it's just a spring compressed with a little wire, two different masses, going to just, you know, show you exactly how fast they're going and that they're basically the same momentum leaves in both directions.
So we're going to redo this experiment now with a car here which is twice.
Okay, so this car, the first experiment, as you can see, they're almost the same number, and that was the two equal mass cars. And so he's just proving the compressed spring divides the energy evenly to the two equally weighted cars. And now he's going to basically show that even if I have unevenly weighted cars, the same half of the force is going to go both ways. The force isn't going to be proportional to the mass. No, the same amount of force goes to the heavy object, goes to a light object. Light object leaves fast, heavy object leaves slow. Force is split in half. Unlike gravity, that gives a huge bias to the heavy things. The heavy things get much more of it, and the light things get barely any of it.
The mass, and this one is 1.
No, girls. I wonder whose idea that is. They always do the girl thing, you know, like 10 to 1, base girls to guys when they show the audience. But yeah, no, I enjoy it, but I'm just saying. It's distracting. For me personally, it's a distraction. As you just noticed, it did distract me, correct? It just, quite obviously did distract me.
So this is the 244, and the one on your right is the 488. So I have to bring them together again with a string.
I probably could have left this part out, but I didn't watch this yet. That's how I'm confident of what the end result is going to be. I'm so confident that, yes, I don't have to even watch it.
So I do the work now. I always do the work here in 26100. I do the work. I squeeze these springs. I get paid for that, by the way. And that's potential energy. If it goes...
Yeah, and you know, enough, and your pension and everything else, and here you are still putting ads on these videos. It's just really tacky. I'm just saying. Pretty tacky.
into the spring.
Why don't you just beg poverty and just say, please send me some money because I need a 50-inch TV, or, you know, some kind of horse. I can, you know, my wife's young. I gotta, you know, keep her in the business. Yeah, I gotta buy her some stuff. You know, send me some money. I do that. Be honest.
Well, it is. Momentum is zero.
All right, so this is kind of the silly part, you know, when they do this whole momentum is zero thing. Well, of course it's zero, but we know that the two objects are going to have momentum when they leave, and the spring has the momentum built into the potential energy. I hate the way they do this, you know, left-right thing, and they say, oh, because the two things, so this one's going this way and this one's going that way, there's zero momentum. No, there's no zero momentum. There's always, just like energy, momentum is always positive. And all you're saying is when the directions are opposing, well, now there's going to be some cancellations possible. But there's no such thing as zero momentum or negative momentum. It's just so cheating perception. I mean, for them to keep claiming, you know, that mv and 1/2 mv squared are somehow completely different equations. Like one of them obviously has a direction and the other one doesn't obviously have a direction. It's just such a lie. There's no arrow over MV. There really isn't. Okay, and you could just as easily put an arrow over 1/2 MV squared. It's just as easy to put an arrow over it. You know, they're the same concept. They're describing the same exact thing. What is the energy? What will it do to the universe? What is it capable of doing to the universe? And that's always going to be this argument. And it's just evil that you people can't get how simple this is. And that this MV squared thing just is messing up the whole game. It's just useless and superfluous. You can do just fine. Follow the momentum. Follow the momentum. Follow the momentum. It'll always, always, always take you down a path that goes somewhere. The kinetic energy formula is lying to you. It's making heroes out of tiny things, you know, in terms of their power. They don't have any of that fake power.
Kinetic energy is zero. I have to zero the timers.
Could just use a scissor, but instead he's using a flame. You know,
oh, and I would like to make a prediction. I would like to see. We'll measure T1, and then we'll measure T2, and then we get a number, and we get a number, and if we multiply this number by 2.00, then I would like to get this number within the uncertainties of the measurements. There is all...
Yes, so it's going to be inverse. So he's doubled the mass, therefore he's going to have the velocities.
Always an uncertainty in any measurement that you do. All right? Make sure that either timer zero.
I mean, all of this just to do this, right? I mean, this is the only downside of his lectures. You know, you can spend hours and hours, and you do say, well, you're sort of cheating me a little. And when you think about it, right, how much time he takes to do the experiments, you know, it's nice that he's doing experiments, but you just think that all you're really getting is math and a lot of bullshit. And, you know, there's a tiny part of the experiment where he actually does it. So, I mean, concepts are so weakly addressed in these lectures, and all he addresses is the gimmicks, the mathematical gimmickry.
Okay, there we go.
Okay, so clearly, what did you get? Yep, half the other. Okay, within the margin of error, exactly half. So it's clearly demonstrating that's what the spring produces. The spring always produces the same momentum. So whatever weight object I put on it, it always produces the same momentum. So if I put a twice as heavy object on it, goes half as slow. I mean, half as fast. It's that simple. PSP guy, or whatever the fuck your name is. All right. So is this experiment evidence enough? I mean, yes, this is not a spring against a wall, but you could understand that it can't theoretically be any different than if I put a spring against a wall. The same exact thing is going to happen. Okay, half the energy this way, half the energy is going to be going into the wall. Just like any other gun or any other mechanism that propels objects. Half the force goes this way, half the force will go that way, and that's all there is. And the half that goes there has to produce the same momentum. He says it. It's always, always, always conserved. Same spring has to create the same momentum. Same compression, same force, same momentum.
What do you see? 406, 193. Whew. On the button. 406 and 193. 0.406, is that what you see? Yeah? And 0.193. Now I don't even need my calculator to multiply this by 2. I can even do that by heart. 9, 3.
He didn't do it by heart. Oops. He says oops. Yeah. So he made a mistake. He do it by heart.
0.396.
I won't get the right answer.
Close enough. The two are in excellent agreement within the 2.5% uncertainty in each measurement. So you see, that's exactly how you can demonstrate the conservation of momentum. They picked up kinetic energy, but after the wire was burned, the momentum remained 0.
So he said the momentum remained 0. Obviously, it wasn't 0 momentum. Obviously, the two objects are shooting off, and one of them has momentum in that direction. The other one has momentum in that direction.
Do you have an aquarium? Well, so do we.
So,
in fact, we have hundreds of aquariums.
You really do have an awful lot. I don't know how this guy makes so much money selling fish. I mean, damn. I used to have aquariums like that. I didn't have that many. I had like 15 at the most at one time. But, yeah. Anyway, yeah, I would like to have a fish store, but I wouldn't like to sell any of them, so I wouldn't be very good at selling fish. But anyway, I'd miss them. You get attached. Yeah. So let's read the dopey comment. Okay. Hell with the dopey commercial. All right, so it says, show me the experiment. I mean, you should be able to come up with a spring experiment. So should you. So let's understand, he has linked to nothing. I've played Physics Girl. I played the other guy, whatever it is, Sumner guy, physics is my business. I played that. I played stuff. Show me that the momentum will be the same for the two bodies. Okay, so I just showed you Professor Lewin overtly saying it's always the same. It's always, 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 always. Okay, and he showed it. Okay, so he says, you are not lying, question mark. So have the experiment that shows that the momentum will be the same where it is, then why don't you show it to me? Okay, so I think I have showed it to you. I think anybody logical knows that if the spring is on two different weights and it still gives them the same momentum, that is, I don't even have like a solid surface. I'm allowing a lighter surface to be on one side, and still half the force ends up in the heavy object. I think I've pretty much demonstrated that the spring always produces the same momentum. Alright, I never said I multiply initial velocity with final velocity, idiot. No, I said that's all you're doing. Putting v squared just means that they took the equation and said, let's do mass times v again. Let's put it in the formula twice. You have to explain why it's in the formula twice. Why would I do that? Oh, in gravity. Yeah, but we're not in gravity. I mean, this experiment isn't with gravity as the force. I just said I use Newton's second law. So again, Newton's second law doesn't say anything about this idiotic equation. We're talking about the utility, the use, the value, the meaning of 1/2 mv squared. It was not invented as a derivative of Newton's. It was invented as an attack against Newton's physics. So let's understand, it was an attack against F equals ma. It was an attack against everything Newton believed. So this is such a lie to say it's some natural derivative. It's no kind of natural derivative. Every time I've seen it derived, I see all this let's convert it into, pollywogs, and then let's turn the pollywogs into giant gremlins, and now let's turn them into green pixies. You're converting things so many times that of course you've made some equalities that aren't really equalities, and that's why you've ended up with velocity in there twice, because you've done dt against dd equals, change in the distance, change in time, change in velocity, and you end up with more than one velocity. Oh, momentum, you end up putting momentum in the force formulas. That's another thing they do. They say F equals momentum. When that's it already. Those two are already equivalent. Momentum is force, is energy. So those things are already equivalent. You've already put them on opposite sides of an equal sign with extra bits. How can there be any extra bits? Momentum is energy. So of course your derivatives are absolute horseshit. Okay, anyway. And they have nothing to do with the creation of this idiotic living force theory. Okay, second law, I'd say that the momentum will not be the same again. So this is just pretty disgusting. You actually think Newton would be on your side. You actually think Newton, if he was alive today, would say, oh yes, Leibniz was quite correct to observe that I was completely wrong. That me and Descartes were idiots. Yes, that's perfectly yes. I have to admit it. I was completely mistaken. Fuck you people. Again, lies and excuses trying to avoid the fact that you don't understand Newton's second law. So again, he says the law says. Professor Lewin just told you the momentum is always conserved. So you can't use Newton's second law to say momentum isn't conserved, or that momentum, the same force, doesn't produce exactly the same momentum, when of course the force is an explosion, or the force is a spring, or the force is a rubber band. Yes, when the force is gravity, then it's true, you're right. One side collects a lot more force. The heavy thing collects a lot more force. But these aren't gravity experiments, asshole. This is what it all comes down to. So just, understand. This is where the formula came from. Dropping objects into clay. This is how they validated this idiotic energy formula. So understand, they thought all the forces in the universe were gravity. They didn't understand the difference between gravity pushing you constantly and a volcano going boom. They couldn't see that those are different things. That an instantaneous, one explosion shooting force in both directions, okay, that can't be distributed. The force is a certain amount of rocks hitting you, right? I explode something and there's 10 rocks on this side flying my way and there's 10 rocks flying your way. It doesn't matter whether I weigh 600 million pounds. I'm not going to get more rocks. It doesn't matter how much I weigh. I get 10 fucking rocks. Your side gets 10 fucking rocks. It doesn't matter. You can't change that. Gravity's different. That's all this comes down to, is these people are too stupid to recognize that forces come in different forms. And different forces affect material objects differently. Okay. The only thing I am saying is that if you use only Newton's second law to solve your problem without using any energy formula, it's so stupid. So he'll never prove that momentum gets the wrong answer. So, but he's implying it. So he's just saying, okay, if I just use the momentum law, he's saying somehow I'll be missing something. All right, using any energy formula, you will see that momentum will not be the same. So again, it's clear that it always is, except in gravity. Okay. If you don't trust solvers, yeah, I don't in any way think you mathematician jackasses know your ass from your elbow, because you can't see something this obvious. I point out how the history is absolute garbage. I point out how the first mathematically it was mv squared. They didn't even have the half in front of it. So it was doubling the energy of everything in the universe. Everything in the universe had twice as much energy as the reality. They were fucking 100% off in their approximation of how hot something was, or how much joules it had. They were doubling the amount. They were so far off. And here you are, a mathematician, and you can't appreciate that? Or you're pretending to be one. And you can't appreciate how awful that formula must have been to be that far off. and you're still trying to defend the horse shit. 70 years they kept a formula that was outrageously exaggerating the energy everything had. 70 years. And then putting the half in, again, doesn't fix it. It just makes it less outrageously stupid. God damn it. All right, well, anyway. Momentums will not be the same. So again, I think I've clearly demonstrated that it's a reliable assertion that the same spring always creates the same momentum, and it can't distribute it in any other way than 50-50. It doesn't have that choice. It has to throw 5 rocks one way and 5 rocks the other. It can't say, oh, you're heavier, I'm going to throw 3 at you. Okay, if you don't trust solvers, then solve the problem on your own. Blah, blah, blah. Doesn't mean anything. Again, I'm for doing clinical experiments that'll get right to the core of whatever your assertions are, because they're wrong. You're the one making these wacky assertions and providing zero evidence for them. Zero. Okay, but it seems you can't. It seems you can't produce any evidence. That's quite obvious to me, and it should be obvious to anybody watching, because you don't understand Newton's second law. So again, he keeps trying to say that Newton thought you should square velocities. Newton didn't think that. So why are you calling it Newton's second law? It's your second law. It's your perversion of Newton. If Newton thought it was a rational derivative, he would have derived it. Okay, you don't link me to a single video demonstrating your bizarre notion. Okay, so well, let's just understand. I just showed it, okay, so let's just, but I've already showed it in other videos, but it doesn't matter. Bizarre notion that the same spring with the same compression will give the 2 different bodies the same momentum. So I just showed that, right? So we should be clear that that was just shown, and it was clearly asserted by Professor Lewin. So go harass him. Go type this kind of shit on his video and see how long it is before it's deleted. Just go ahead and try writing this kind of crap on his video and see that he's not going to appreciate it either, douche. That your argument is too thin. If you could make a better argument, then maybe somebody could stand your rudeness. But your argument sucks, and you're a rude little putz. Not a good combination. So clearly, I have debunked that last sentence. I've clearly done enough, right? You don't link me to a single video demonstrating the bizarre notion. He says it's bizarre that the same spring with the same compression will give 2 different bodies the same momentum. Clearly, that's exactly what they do. All right. So, that's enough. I could play, I guess. I could go see what else Professor Lewin's going to say.
I own a fish store. I've got a whole building with
okay.
fish rooms.
You're doing good. Lucky you. Yes, I don't know if he's going to say anything here.
The topic. It appears that I changed the topic, but you will see in a few weeks that it's really related. Not even a few weeks. You will see that it's really related.
Oh, he's doing Gauss's law or something.
And this is the position vector R of this equation. It gives me the BDT.
Yeah, this is
so in the x
kind of
direction,
Gaussy stuff.
Of course, the same equation holds for the...
Okay, so anyway. That gets quite convoluted. Anyway, so that's enough and such. Oh, I don't do it that way. I'll do it the professional way. Alright. I don't think we have to add anything, right? Don't think so. Alright, this has been a DraftScience video presentation. Thank you for your... what, really? Do I have to thank anybody? Well, I thank the guy. There's 1 or 2 of you that's worth thanking. But yeah, the rest of you, I don't think so. I don't think you're doing anything. You're not making, I was going to say participation, but there is no constructive participation, really. And, yeah, so I don't think I'll do that thank you thing anymore. So, just get what you deserve. That's it, yeah. Get what you, I wish that you all would get what you deserve. I really, really do wish that you get exactly what you deserve. Exactly. Measure for measure. The full momentum of your earnings, okay, should be deposited upon you. Alright, now that's enough. And such. I might as well do it again. Yeah. Till next time. Such.